Welcome to Chapter 10, Section 4. My name is MathYou, and we're going to be talking about mathematical induction in this video. I'm going to go through some slides that were adapted for Blitzer's Precalculus 3rd edition book. And in this section, I'm going to, the structure of the video is that we're going to look at some definitions and some examples and some workflows, and I'm going to work through in detail some solution processes. And a key component of that, in this video, I'm going to do something unusual. I want to tell you something that we're going to talk about later in the section, but that it's so important I want to point it out right now before it becomes the thing that's slotted into the middle of a bunch of other information. And it's going to sound a little weird out of context, but let's give it a shot. I'm going to give you at some point an n value. Okay, I'm up here toward the top left. Oh, I can't write between pages, so I'm not going to go there. I'm going to go... Where am I going? We can do it over here, under the date. I'm going to give you an n value, and we're going to be working with an equation. And if n is equal to 1, then I'm only going to have one thing over here, one term. And over here, there's going to be an expression, like a formula, okay? There's going to be some stuff going on over here on the right-hand side of the equation, and that's always going to be true. And when n is equal to 1, on the left-hand side of the equation, you're only going to have one term over here. When n is equal to 2, it's this important. This looks really elementary, but it's this important. When n is equal to 2, you're going to have the same stuff on the right-hand side of the equation. Same thing. But on the left-hand side of the equation, you're going to have two terms. Terms are things that are being added or subtracted. Okay? So on the left-hand side of the equation, you're going to have two things that are being either added or subtracted. When n is equal to 3, guess how many things you're going to have, guess how many terms you're going to have on the left-hand side of the equation. That's right. And 4 and 5. What if I told you that on the left-hand side of the equation, what if I told you that n was equal to r? R is a number. It's an integer. When n was equal to 1, you had one term on the left-hand side. When n was equal to 2, you had two terms on the left-hand side. 3 terms on the left-hand side. When n is equal to r, you have r terms on the left-hand side. R is just some undisclosed number. What if I told you n was equal to r plus 1? How many terms are there on the left-hand side of the equation? R plus 1 terms. What's that going to look like when I have r plus 1 terms over there? Well, it's going to look like this. I'm going to have a term here, and then it's going to be added to another term here, and then it's going to be added to a bunch of other terms, ... Actually, I'm going to slide this over just a little bit. I want a little bit more room. So everything is the same. You're going to have a term, plus, a whole bunch of other terms, I don't know how many, plus the rth term, plus the r plus first term. So again, it's strange to have to wedge it into this space, but here you're going to have r terms. 17, 17,000, 17 million, I don't know. R terms. And here's the extra term, right? This one. This one is that extra term. It's the r plus first term. So if r was equal to 23, then this would be the 23rd term. This would be the 23 plus 1th term, in other words, the 24th term, and 23 plus 1 would be 24, so n would be 24. All right? Whatever this n value is, that's how many terms you're going to have on the left-hand side of the equation. All right, I told you I was going to tell you something. And that's true, except I told you the same thing like 6 times. I'm going to bring it up again later. Now let's get started. The principle of mathematical induction. Two things are going to happen in order to prove that a particular statement is true for all positive integers n. And when I say all of them, I mean all of them, from 1 all the way out to infinity. All of them. And all I have to do is demonstrate 2 things, and then, by the principle of mathematical induction, I will be able to say that that statement is true all the time. The first thing I have to do is prove or demonstrate that the statement is true for an n value. I can't use a black pen, it's terrible. Here in the top left under the P in principle, first I have to show or demonstrate that the statement is true when n equals 1. And then I'm going to make an assumption. I'm going to assume that the statement is true when n equals k, like n equals r from up here. Where'd it go? Well, n equal to r, or r plus 1 up there. Now I'm saying that we're going to assume the truth of the statement when n equals k. We don't know what k is, but it's a number, it's an integer. We're going to use that assumption to prove the truth of the statement when n equals k plus 1. There's a very distinct possibility or probability that you as an individual who are listening to this video right now have no idea what I'm talking about. I'm going to prove that the statement is true. You're glancing down maybe, that the statement is true when n equals 1 and then when n equals k plus 1. Let's just try it, okay? We're not doing the entire process in this first example. We're simply getting used to a little bit of the language. So what's the statement? Generally, the statement is this. That's the generic nth version of the statement, is that 3 is a factor of n to the third minus 1. When n equals 1, so here's s sub 1, statement with an n value of 1. 3 is a factor of 1 to the third power minus 1, which is 0. Is 3 a factor of 0? That's weird. Let's go to the second statement. We'll come back to it. Leave a blank line or two there. S sub 2. 3 is a factor of... Now we've got an n value of 2 to the third power minus 2, bad 2, which is equal to 6. Is 3 a factor of 6? Most of you are thinking yes. You're not saying it out loud, though. You'd never say it out loud. Somebody might hear you, and you might be wrong. But in this case, you're right. 3 is a factor of 6. What does it mean to be a factor of 6? What does it mean for 3 to be a factor of 6? It means, in other words, 3 times something, some integer. I don't want to use r again. Can we use p? Let's use p. I'll say it a little bit formally. There exists an integer p such that 3 times p equals 6. Now 3 is a factor. Why is it a factor and it's not a term? Because it's connected to p by multiplication. Factors are connected by multiplication. Terms are connected by addition or subtraction. Okay, so 3 is a factor of 6 because I can take 3 and multiply it by some number and get 6. Okay, and it's true, I get it. 3 is a factor of... This is true, right? I'm going to put a check mark next to it. That's a true statement. Let's back up one now. In other words, 3 times some p-value, some other p-value, I shouldn't really use p again, is equal to 0? Really? I could put a question mark next to that. That's what I'm really asking here. Is this true? Does there exist a p-value such that 3 times p equals 0? Yes. P-value of 0. Just like here, it was a p-value of 2. Let's try s sub 3, just to really drive the point home. 3 is a factor of n value is now 3 to the third power minus 3. What does that equal? 27 minus 3. That's 24. Is 3 a factor of 24? Can I take 3 and multiply it by something, an integer, and get 24? Yeah, 8. So the p-value would be 8 in that case. So the answer to this one, it's not so much the answer to that one. We're just writing out the statements. What I'm pointing out to you is that all of these statements are true. So we've demonstrated that s sub 1, 2, and 3 are true. Does that mean necessarily that s sub 4 is true? It does not. Maybe it's a coincidence that it worked for the first 3 and it doesn't work for any of the rest of them. We need a method to prove that it's going to work for all the rest of them. And that's a proof by mathematical induction. The steps are pretty much what we just did. We show that it's true for s sub 1, and then we show that if s sub k, the kth statement, is assumed to be true, so that's going to be our assumption, then the subsequent statement, s sub k plus 1, where n is equal to k plus 1, will show that that's also true. So assuming s sub k will show that s sub k plus 1 is true. All right, let's give it a shot. Here's the first instance of that strange topic that I talked to you about at the beginning of the video. Show true for n equals 1. For n equals what? 1. N equals 1? Yes. You're losing it. I lost it a long time ago. N equals 1. So how many terms am I going to have on the left-hand side of the equation? 1. When n equals 2, I'll have 2 terms. When n equals 3, I'll have 3 terms on the left-hand side of the equation. But at the moment, I've only got 1. Look up here with me. 4 plus 8 plus dot, 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 all the way up to 4n. How many terms are there right there? That's a 2, by the way. That's a 1. That's a 2. What comes next? 3, 4, 5, all the way up to 4 times n. I think we can safely say that there are n terms right here. And what's the first of those n terms? Please tell me that you're thinking the number 4. What's the first term on the left-hand side of this statement right here? What's the first term? It's a 4. And when n equals 1, and we only have 1 term on the left-hand side of the equation, which term do you think we should use? Please say the first one. Great, let's use the first one. So what does s sub 1 look like? It's an equation that has 1 term on the left-hand side. And the right-hand side equals the squiggles that I wrote at the top of the very first page of our notes. In this case, it's not squiggles, it's actually 2n times n plus 1. Oh wait, we know what n is. I'm so hung up on the fact that there needs to only be 1 term on the left-hand side of the equation. I forgot to take this n value of 1 and put it into this position and this position. So let's do that. It actually equals, the right-hand side of this equation actually equals 2 times 1, which is our n value, times 1 plus 1. That's a lot of parentheses, but it works. Is this true? Does 4 equal 2 times 1 times 2? Yes. Have we shown that S sub 1 is true? Does 4 equal 4? Yes. So step 1 is complete. Don't actually write this down, but have a look. If we wanted to write out S sub 2, I would have an equation. And the right-hand side would have some kind of formula-looking thing on it. This stuff up here. It would have some formula-looking stuff written on the right-hand side. And on the left-hand side would be some terms. And when n is equal to 2, how many terms do you think there are going to be on the left-hand side? 2, that's correct. And which 2 terms do you think we should use from up here? How about the first and the second terms? It's like rocket science. And S sub 3 would have 4 plus 8 plus waiting. 4 plus 4 makes 8. 8 plus 4 makes 12. 12! 4 plus 8 plus 12. We'd have 3 terms on the left-hand side for S sub 3. Okay. I don't want you to write that down because that's not part of the process. We're only supposed to start out by showing that it's true for S sub 1 up here at the top of your screen. Okay, let's do step 2 now. Show that if S sub k is assumed to be true, what does that look like? When n equals k, then we're working with the kth statement. And how many terms will there be on the left-hand side of the equation? K terms. When n was 1, there was 1 term. When n was 2, there were 2 terms. When n was k, there were k terms. And what do those terms look like? How do I describe k terms? Have a look up at the top of this example. Prove using mathematical induction 4 plus 8 plus some unknown number of terms in the middle plus 4 times k equals 2 times k plus 1 because n equals k. So we replaced all of the n's in our formula with a k. K terms on the left-hand side. Okay. Okay, so we've made our assumption. Then, at the very top of your screen, it says we need to show that S sub k plus 1 is also true. By the way, there are other videos, and as a matter of fact, I think the author of the book that goes along with these notes, or that these notes go along with his book, I think that Stewart actually presents this process using a different method. As far as I recall, I've only seen 2 methods for solving using mathematical induction, so just be aware that there's another process that's out there, and you'll see a lot of, if not all of, the same elements in that process. They're just presented in a slightly different way. Show true for n equals k plus 1. Well, what is the k plus first statement? Well, it still has the first term, and it still has the second term, and it still has a bunch of other terms. There should only be 3 dots there, dot, 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 plus there are k plus 1 terms. It's still going to have the kth term, that should say 4 times k, but it's also going to have a 4 times k plus 1 term. That's the k plus first term. Now remember, in this statement, n equals k plus 1. So we have made it all the way up to this n value now being a k plus 1. Now we have to change this n value to a k plus 1 and this n value to a k plus 1. Now my use of parentheses doesn't look as much like an overuse of parentheses. Up here it looked a little overwhelming and a little silly, but down here, very valuable. Okay, so we're supposed to use the assumption, and as a matter of fact, you must, in order for this to be a legitimate proof by mathematical induction, you must use the assumption. And we're going to use it right away in this problem. Notice, please, that works. Do those terms look familiar? Look up 2 lines. They should look very familiar. Identical. Those k terms. So what I'm going to do is I'm going to swap these k terms, I'm going to swap them out for something of equal value. Can you think of anything that 4 plus 8 plus ... plus 4k is equal to? It's equal to 2k, k plus 1. So I'm going to do substitution, which is a process that you're familiar with. I'm going to substitute 2 times k plus 1 for those k terms. Don't forget you do still have to add on the k plus first term. And supposedly, I'm going to put little question marks in here. Supposedly, or what we're trying to show, is that the left-hand side does indeed equal the right-hand side. A proof like this requires you to leave one side of the equation alone and to only modify the other side of the equation. So in this case, we're going to leave the right-hand side of the equation as it is, and we're going to manipulate the left-hand side until it looks just like the right-hand side. It's not going to take very long. We now have 2 terms, this term and this term. Those 2 terms share some common factors. There's a multiple of 2 right here, and inside of that 4, there's a multiple of 2. There's also a multiple of k plus 1 and a multiple of k plus 1. So I'm going to take out those 2 common factors. That was a 2 times a k plus 1. And after I take the 2 and the k plus 1 out of here, and half of the 4 and the k plus 1 out of here, what am I left with? A multiple of k and a plus 2. And wouldn't you agree, if you need to pause and make sure that you're on board as of that last line, 2k plus 1, k plus 2, as long as you're okay there on the factoring, because that's what we did. And in order to go from this line down to this line, we use substitution. Actually, I'm going to write use assumption. You have to make it fit on your own notes. So this bracket that we used right here was us using the assumption. So let's take it from the top. We started with this statement, the k plus first statement. By assumption, we were able to substitute in this statement, the 2 times k plus 1. By substitution, using the assumption, we arrived at this line right here. And in order to go from that line to the next line, we did some factoring. We factored out some common factors from those terms. That took us to here. And then in order to go from here to here, we're going to do something a little silly. Left-hand side equals the right-hand side. We've shown that assuming the truth of the kth statement, we will be able to prove the k plus first statement, no matter what the k value is. You can put me, I always imagine it like it's a set of stairs or a pathway with, defined stepping stones or something. So I might say something like, you could put me on the 73rd step. And I don't know how you got me there, but I know that if I'm on the 73rd step, I will be able to make it to the 74th step. That's what we just proved. If I'm on the kth step, I will be able to make it to the k plus first step. So if I'm standing on 1, I'll be able to make it to 2. If I'm standing on the second step, I'll be able to make it to the third, and so on forever. So we have proven that this statement up here is true for all integer values of n. Often, you'll see, even in textbooks, a little shaded in box at the end of a proof like this, or at the end of any of the proofs or declarations that are made that you've seen most frequently in textbooks or ebooks. And this little box is like a mathematical punctuation mark. Or maybe a mathematical mic drop, right? Because you really just showed that problem who's boss. So, treat yourself. Prove using mathematical induction. Step 1. Let's pick up the pace a little. Let's spell it correctly. Step 1. Show true for n equals 1. We're going to have an equation. There are potentially going to be a bunch of terms over here, and on the right-hand side, that's my squiggly mark, right, with my equal sign and then all my terms on the left-hand side. And when n is equal to 1, how many terms are there on the left-hand side? Only 1. Which one of these terms is going to appear on the left-hand side? How about the first one? Okay, so 1 divided by 2 times 3 is supposedly equal to, we're working with an n value of 1 here, so we've got 1 over 2 times 1 plus 4. Does 1 over 6 equal 1 over 6? Sure does. So we've satisfied step 1 of the proof by mathematical induction. Step 2. Assume true for n equals k. So we're assuming that we've made it to the 73rd step, and then we're going to show that if we're there, we can make it to the 74th step. I'm using 73 and 74. Those are arbitrary. I don't know where those came from. What does the kth version of this statement look like? It looks just like that statement, except the n's are replaced with k's. 1 over 2 times 3 plus 1 over 3 times 4. I'm going to skip that next term. Well, I'm not going to skip it. I'm just going to include it in my dot, dot, dot. Plus 1 over k plus 1 times k plus 2 is supposedly equal to k over 2 times k plus 4. That's what the kth statement looks like. By the way, how many terms are there on the left-hand side of that statement? Please say k. K, that's correct. Now that we've made that assumption, we will prove true, or show true, for n equals k plus 1. In other words, 1 over 2 times 3 plus 1 over 3 times 4 plus all those terms in between, plus, be careful now, this is the kth term that we're going to write, 1 over k plus 1 times k plus 2. Now that's if there were k terms on the left-hand side of the statement or equation. There are not. There are, I didn't write the 1 in there, I just wrote it. There are k plus 1 terms on the left-hand side. So, if these are the first k terms, now we need the k plus first term. here's my, ooh, that's too big. There's a k value. Actually, those aren't k values, those are n values. We've changed n into a k in those two instances. Over here to the right of that, we've changed n into a k plus 1. Why would I change an n to a k plus 1? Because that's the statement that we're working on, the k plus first statement. Why am I writing out both of these terms? I'm going to show you, I promise. We're going to move from this, oh, we need the right-hand side of this equation first, sorry. Previously, the right-hand side of this equation said k over 2k plus 4. Now, instead of having changed an n into a k, we're changing n into a k plus 1. So our numerator there is k plus 1, and our denominator says 2 times k plus 1 close plus 4. So the k has become a k plus 1 everywhere. All right, so this is the equation that we're trying to prove, so I'm going to put a question mark there because we don't actually know that those two statements are equal to each other yet. The next thing that I'm going to do to try to prove that they're equal to each other is I'm going to manipulate the left-hand side of this equation until it looks exactly the same as the right-hand side. And the first thing that I'm going to do in order to make that happen is I'm going to do some substitution again. By substitution of the assumption, I can write this. Those are identical. And the one that I wrote at the top of the screen is equal to this stuff. So that's what I'm going to substitute in place of those k terms, just like we did in the previous problem, actually. If you want to use a highlighter, I do this in the classroom actually, and I can't erase it like I can with this digital pen, but I do this. I highlight that, and I highlight this, and I highlight this, and I highlight this. Because those are the same statement. At the top of the screen, you've got the left-hand side and the right-hand side of the statement. And then here you've got the left-hand side, and then here you've got the right-hand side, and you can swap them out because they're equal to each other. So if you want to leave those highlighted to help you when you're reading your notes again later, you should do that. And in the next term, right, I've changed all of these terms into this one term, so it shouldn't be unreasonable that I'm now going to change this into something. I'm actually going to change only the denominator of this fraction. And the way that I'm going to change the denominator is I'm going to factor out, can I do that? Something looks wrong. I'm not going to factor. K plus 2, K plus 3. I can't actually remember how this problem plays out, so it's like we're solving this together for the first time. Oh, I don't think I want to be in blue, though. So let's just go with it. When in doubt, when you're not sure what to do next in these problems, do something that you know you're allowed to do And this is a recommendation that I have given for those of you who are my students in person. You've heard me say before, sometimes you're not going to know what to do next. So just do something that you know you're allowed to do based on the rules of mathematics. And in this case, I know that, I will use blue for a second, that I can add these ones together, and I can add the 1 and the 2 together. So essentially I'm combining like terms. So if you want to put CLT somewhere for combined like terms, you may. This turns into a k plus 2. This turns into a k plus 3. And that may or may not equal the right-hand side, and we're trying to figure that out. Now what am I supposed to do? Well, geez, I don't know. And that's fine. So what should you do? Do something that you know you're allowed to do. How many fractions do you have on the right-hand side of this equation? 1. How many fractions do you have on the left-hand side? 2. You figure we need to turn those 2 into 1? Absolutely. How are we going to do that? Addition. Can you add fractions together? Absolutely. But what do you need? Right? This is not new information. You need a common denominator. So let's make a common denominator. I'm going to do something first. If you want to rewrite this entire line, you can. It's not a bad idea. But what I'm going to do, the only thing that would change if I rewrote this, is I would change this denominator and write it as 2 times k plus 2. I would factor it. This denominator over here is factored, so I'm factoring the one on the left. It's going to make it easier for me to find the common denominator. And the common denominator will be 2 times k plus 2 times k plus 3. So we'll take our first fraction, and multiply it by the only number you're allowed to multiply it by, 1. Anything divided by itself is equal to 1, right? So we just took that fraction, multiplied it by 1. Changes what the fraction looks like, but it doesn't actually change its value. That's why we're allowed to do it. In this fraction, we're going to multiply by a different version of the number 1, 2 over 2. Some of you are watching this video thinking, dude, I do not need to know how to make common denominators. And some of you, don't forget, there are some people who are saying, thank God he's showing me how to make common denominators again. I always remember when I see it, when somebody walks me through it, but sometimes I have trouble remembering it off the top of my head. So since we have a common denominator, 2 times k plus 2 times k plus 3, 2 times k plus 2 times k plus 3, those two fractions have the same denominator. I'm allowed to add their numerators together. And k times k plus 3, if you distribute, you get k squared plus 3k. And then there's the 1 times the 2 gives you the plus 2. Where'd the plus come from? It's right here. Those are the same plus signs. So just making sure that you're on board with all where all those things came from. The question remains, does this equal the right-hand side? It was so long ago, the right-hand side's almost off the screen. I'm going to factor my numerator, which becomes k plus 1 times k plus 2, still over the denominator. Still maybe equals the right-hand side. Definitely the k plus 2 and the k plus 2 are going to cancel each other out. If we have to go on to the next page, we will. So now we've got k plus 1 in the numerator over. In the denominator, I'm going to distribute. I'm going to write this as 2k plus 6. So we distributed in the denominator, we got 2k plus 6. Maybe this equals the right-hand side. I tell my students that when the left-hand side blatantly, obviously equals the right-hand side, that you should stop. Does it blatantly equal the right-hand side? Well, in my mind, I'm looking at the right-hand side in the top right corner of my screen, and I'm saying, well, that's 2k plus 2 plus 4. Oh yeah, 2 plus 4 is that as soon as you have to say, if it takes you more than one step to solve the right-hand side or to make the right-hand side look like the left-hand side, I say keep going. Be just kind of insanely neurotic about it. It takes the tiniest bit of cleverness to continue modifying the left-hand side so that it looks even more like the right-hand side. For example, we're now going to write our denominator as 2k plus 4 plus 2. Maybe that still equals, maybe that equals the right-hand side. And then now for sure I have to go on to the next page. In my denominator, I'm going to factor, but I'm only going to factor a 2 out of these two terms so that I end up with k plus 1 over 2 times k plus 2 plus 2. Please, 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 does that equal the right-hand side? I don't even know where the right-hand side is anymore. Why does that say 2 times k plus 1 plus 4? Oh, this was supposed to say k plus 1, so I just made a mistake. Easily fixed. All right, so the mistakes were here and here. This should have said plus 2 plus 4. If I had seen the right-hand side of the equation, if it was all on the screen at the same time, I don't think I would have made that mistake, but it's okay. We're human. Now I am still going to do this bit of factoring here. Taking a 2 out of those two terms leaves me with 2 times the quantity k plus 1. And then that 4 comes down. We didn't touch that. Now this does legitimately look identical to the right-hand side, which means, for starters, that we can put our little shaded box saying that we have completed the proof. It has been shown. It has been shown. He says the weirdest things. What's been shown? It's been shown that this statement is true for all n values that are integers. All infinitely many of those statements are true, or would be true, or will be true, or however you want to say it. That's pretty impressive. This problem, interestingly, is very similar to the very first example that we saw in our notes in this section, where 3 was a factor of something. Now 2 is a factor of something. And what did it mean to be a factor of something? Is 2 a factor of 12? Yes. Why? Because 2 times something else can equal 12, or does equal 12. So that's what it means to be a factor of. And when we were talking earlier in these notes, I used the letter P twice. And I said, I shouldn't really be using P again, because in this second statement, P is going to take on a different value. So we're not going to reuse our, it's not a variable. It's a constant, right? P was representing a specific number, so it's a constant value. So in this equation, I think we're going to have a P and maybe a Q, all right? So that we're sure that that those are two different constant values. All right, let's give it a shot. Step 1. How much space do we have for this? Well, we've got the whole page, and then that's it. All right, so step 1, show true. For n equals 1. In other words, 2 times, let's say, P equals 1 squared minus 1. In other words, we're trying to show that 2 times some number P is equal to 0. And based on our conversation earlier, we know that that's true. A p-value of 0 would satisfy this statement. So, check mark. In a very formal proof, if you were in a math foundations course, if you were in like a math class that numerically was like 299 or 2999, right? The highest level, low level undergraduate math class, this could be written up even more formally. You would want to have a declaration statement that says that p is an integer, and we could include that. Show true where n equals 0. Where p is a member of the set of integers. Couldn't we have just written where p is an integer? Yes, but for those of you who are going to be going farther through your study of maths, well, now you've seen that notation. And then we can put a check mark because that worked. Step 2. That's not, I don't know what language that was. Step 2, assume true for n equals k. All right. In other words, 2 times some other integer will equal k squared minus k. Previously, it was 2 times some number p will equal 0. This time, it's 2 times some different number, q, that will equal k squared minus k. It's like a lowercase c with, this one was better over here, really. It's like a lowercase c with a little shelf in the middle of it. You know, you could, if you had this in your living room, you'd probably come in here and put a little succulent or something in here. Just a little horizontal line that's in there. That's what you thought I was going to say, right? Just a little succulent. Why does that keep drawing? Okay, so we're assuming true for n equals k, so 2 times some number q equals k squared minus k. Now, show or prove true for n equals k plus 1. In other words, show there exists some integer I'm running out of letters, p, q, r, some integer r, such that, do we have room over here? Nah. Such that 2 times that integer r will equal k plus 1 squared minus k plus 1. Originally, it was 2 times some number equals n squared minus n. That became 2 times p equals 1 squared minus 1. Then it became 2q equaled k squared minus k. And now it's 2 times some other integer equals k plus 1 squared minus k plus 1. So the n value keeps changing. It went from an n value of n to an n value of 1 to an n value of k to now an n value of k plus 1. Okay, we're supposed to show that that's true, and the law says we must use our assumption. I'm staring at this thing down here, wondering, we've done substitution so many times already in this section, am I going to be able to use substitution again? What would I substitute even if I could? Here's the assumption, that's what I have to use. It's got two sides to it. I don't see a 2q anywhere in here that I could substitute it in. What about a k squared minus k? Do you see a k squared minus k in here? Sort of. Let's move some things around and create a k squared minus k so that we can do the substitution. I FOILed and combined like terms to get k squared plus 2k plus 1. Then I'll distribute the minus sign, so I get minus k minus 1. And then I'm not combining like terms right away. Remember why we're doing these first couple of initial steps is that we're trying to create a k squared minus k. And I see them now. K squared minus k squared minus k. Let's just take those two terms and slide them over next to each other, and then we can do whatever we want with the rest of the stuff. I think I'll combine the plus 1 and the minus 1. Those are the only things left, right? We pinned down our k squared minus k because we want to use that. And then what was left? A plus 2k, a plus 1, and a minus 1. Well, we're bringing the plus 2k with us. There's nothing else to combine that with, but the plus 1 and the minus 1, I'm going to combine those. If we have to bring them back later, we will. Now, by assumption and substitution, if you want to write that, I'm going to bracket this. You don't have to do this. If that's going to look confusing to you later, don't do that. But I'm replacing, that's where the substitution is happening, and I'm replacing it with a 2q. And I'm bringing the 2k with me. And don't forget, the left-hand side of this equation says 2r. We're supposed to be showing that there exists some integer r such that 2 times that integer will equal the right-hand side, which now looks drastically different than it did in the beginning. I factored out a 2 from both of those terms. You're never going to believe what I'm going to do next. Well, maybe you will, maybe you won't. I put my shaded in box. You might be thinking, wait a second, you're right, I don't believe you. The left-hand side does not look like the right-hand side. What were we trying to find? We were trying to find or to show that there exists some integer r such that 2 times that integer equals 2 times some integer. Is q plus k an integer? What's q? It's an integer. And what's k? Do we have a note about what k is? Oh, k has to be an integer because n is an integer, right? We were marching through these n values, and n was either a 1 or a 2 or a 3 or a 4. They're positive integers, actually. So k is definitely also an integer. And an integer is like -3, -2, -1, 0, 1, 2, 3. It's the whole numbers, we used to call them when we were kids, but that turns out that was wrong. Whole numbers are 0, 1, 2, 3. But the integers include the negative versions of those. And what do you get when you take an integer plus another integer? I'll spare you the suspense. You get another integer. Therefore, q plus k is an integer. It's the integer that we were looking for. We were trying to find an r value, show that there exists some integer r. We found it. What is it? It's q plus k, which is understandably a little anticlimactic. We don't actually have to prove what the integer is. There's almost no numbers in this whole thing that we're doing here, right? We're working with p's and q's and k's and n's and r's. We're not trying to find the specific r value. We're just trying to show that there exists an integer r. And we've done that. There are lots of examples out there, I'm quite sure, where other proofs by mathematical induction are worked out. Let me remind you that there are, at least in my experience, 2 different processes for demonstrating something or proving a statement by mathematical induction. So watch out. If you're watching a video and it seems like, whoa, I didn't see anything like this when Newbeck was teaching his on that other video that I watched, don't be surprised. Make sure, I don't know, I'm a big fan of showing all of my works. Make sure that you're finding somebody who's giving you good explanations as to why you're doing the things that you're doing as you're going along. And that's all I've got for you. And in this chapter, there's only one more section, so I'll see you in 10.5. Thanks so much.